In this unit, we are going to look at thermodynamics and a branch of thermodynamics called thermochemistry. And in this lesson, we're going to discuss a lot of the terminology that's going to be used throughout the unit. Thermodynamics is the study of energy changes in various systems, such as phase changes, chemical reactions, and nuclear changes. Thermochemistry, a branch of thermodynamics, is the study of the energy changes that's associated with chemical reactions. It is very important since everyday energy is used in the form of heat, like fossil fuels, light, like fireflies, mechanical, like internal combustion engines, and electrical batteries. Energy is the capacity to do work or to supply heat. Temperature is the measure of the average kinetic energy of the particles in a system. It is independent of the amount of material present. Kinetic energy is the energy of motion. We discussed kinetic energy in the kinetics and equilibrium unit. It is the result of the movement of particles. And the average kinetic energy differs between gases, liquids, and solids. Gases having the most kinetic energy, and solids having the least amount of kinetic energy. Potential energy is the energy due to condition, position, or composition. More or less, it's stored energy and the potential for kinetic energy. Thermal energy is the kinetic energy associated with random molecular motion, and it is proportional to the temperature. Work, which is denoted by a lowercase w, is the energy exchanged by a mechanical means. It involves the application of a force that is associated with the movement of an object by a specific distance. For example, if I decided to move my desk across the classroom, work will be done. Heat, which is denoted by a lowercase q, is thermal energy that is transferred between objects when a difference in temperature exists. Heat does depend on the amount of material that is present. Heat is always transferred from a hotter object to a colder object. The temperature of the hotter object will therefore decrease, while the temperature of the colder object will increase until both objects reach the same temperature. Once they reach the same temperature, they're considered to have equilibrium temperature. The hotter object originally possessed a greater average kinetic energy since it had a greater temperature than the colder object. The kinetic energy is transferred from the object with the greater kinetic energy to the object with the lower kinetic energy until they have the same kinetic energy, and again the equilibrium is established. This process occurs for objects that are in close thermal contact. So for instance, if you were to hold the hand of someone who has a colder temperature, your hand will decrease in temperature, their hand will increase in temperature until you both have the same temperature. Since we're going to be studying the transfer of heat in this unit, we have to look at the difference between a system and its surroundings. A system is the part of the universe that we choose to study. So any chemical reaction in which we decide to study will be considered our system. A chemical system is that substance or a group of substances that are undergoing a change. For instance, if I was to drop an ice cube into a hot cup of water, I would be studying the ice cube because the ice cube would be undergoing the change. The surroundings would be the part of the universe in which the system interacts. In my example, the ice cube will be interacting with both the hot water as well as the glass walls of the container that the hot water is in and the air on top of the glass. The first law of thermodynamics states that a system does not possess or contain heat or work. Heat and work are the means by which a system exchanges energy. Heat and work exist only as changes, and it's represented by a delta T for heat, and delta meaning a change in, or delta position for work. The energy contained within a system, in the form of chemical bonds, intermolecular attractions, and kinetic energy, is known as the internal energy, which is represented by a capital E. Therefore, the first law of thermodynamics states that a change in energy is equal to both the heat and the work. Energy entering a system is associated with a positive sign, meaning it absorbs heat, and we know from kinetics and equilibrium that this is an endothermic process. If we have a system that releases heat, that is associated with a negative sign, and we know this to be an exothermic process. In interactions between a system and its surroundings, the total energy always remains constant. This is known as the law of conservation of energy. The law of conservation of energy states that energy is neither created nor destroyed, but it can be converted from one form to another or transferred between a system and its surroundings. So overall, the heat of the system and the heat of the surroundings will always equal 0, since it cannot be created nor destroyed. Therefore, the heat lost by a system must be gained by the surroundings and vice versa. We can represent this as Q, or heat of the system, will be equal to negative heat of the surroundings to show that energy transfers back and forth, or that the heat lost will be equal to the heat gained. There are 3 different types of systems: an open system, a closed system, and an isolated system. An open system is a system where both energy and matter can be transferred between the system and its surroundings. An example of this would be an open beaker of hot water. An open beaker of hot water can lose heat to the surroundings upon cooling, and it can lose matter in the form of water vapor. If we were to consider this as system versus surroundings, the system that we're studying in this example would be the hot water, the water molecules. The surroundings of the hot water in this example would be the beaker, the walls, the glass walls of the beaker, and the air on top of it. So the system that we're studying here are the water molecules inside of the beaker. The surroundings would be the walls of that beaker, as well as the air that can enter on the top of the beaker. The second type of system is a closed system. In a closed system, energy can be exchanged between the system and its surroundings, but matter cannot. An example of a closed system would be a stoppered Erlenmeyer flask of hot water. The stoppered flask of hot water can lose heat to its surroundings through the walls of the Erlenmeyer flask, but the water vapor cannot escape since it's stoppered. Again, in this example, the system that we're studying would be the water molecules inside of the Erlenmeyer flask. The surroundings will still be the walls of the Erlenmeyer flask, as well as any air that's inside of the flask. The last type of system is an isolated system. And in an isolated system, neither the energy nor the matter can be exchanged between the system and its surroundings. An example of this would be a vacuum flask or a thermos of hot water. A thermos of hot water is not exactly an isolated system, but it does approximate an isolated system and is more like an isolated system than it's like a closed system. In this case, the system in the vacuum flask would be whatever liquid contents are inside of the flask or the thermos. The surroundings would again be the walls of this thermos and the air around it. It is very important that you practice identifying the different types of systems, as well as, given an example, be able to identify what would be the system and what would be the surroundings. Therefore, I strongly encourage at this time that you practice this with the worksheet.